So in the previous module, we introduced this table. In this module, we're going to work through the first three groups on this table. We're going to work through linear, trigonal planar, and tetrahedral electron domain geometries and the corresponding molecular geometries that come from that. And we'll work through a few examples of each of those. So a little refresher on the steps, right? The first step, draw the Lewis structure. Okay, I have ammonia. Well, nitrogen has 5 valence electrons. Hydrogen has 1 each, and I've got 3 hydrogens, so I've got 3 valence electrons there. I've got a total of 8 electrons to assign. So there's my central nitrogen. I just assigned 1, 2, 3, 4, 5, 6 electrons, right? I had 8 total, so 2 more, 1, 2. So I've assigned 6 total electrons. There's my Lewis structure for ammonia. Now I need to determine how many electron domains that I have. Well, I have 1, 2, 3, 4 domains. So based on having 4 electron domains, my electron domain geometry is tetrahedral. My last question is, how many of those domains are bonding and non-bonding? So I have 4 electron domains. Right? That means I have a tetrahedral electron domain geometry. Of those 4 electron domains, 3 are bonding and 1 is non-bonding. So based on that, I am trigonal pyramidal. I have 3 electron domains that are bonding and 1 non-bonding, and that would give me the geometry of ammonia. So our Lewis structure, count electron domains, and then of those counted electron domains, determine which ones are bonding and non-bonding to find the electron domain geometry first and then the molecular geometry next. As you'll notice, the electron domain geometry and the molecular geometry are not always the same. So in this case here, if all 4 domains were bonding domains, then yes, my electron domain geometry would be the same as my molecular geometry. That does happen, but it does not happen every single time. So for the easiest electron domain geometry, right, the linear. If I have 2 electron domains, with those 2 domains and only 2 domains, right, the best arrangement in space is a linear arrangement. That puts both of those domains 180 degrees apart. So if we see something that's linear, right, it's going to have bond angles of 180 degrees. That's because there are only 2 electron domains, and the best arrangement in space for those 2 electron domains is a linear geometry. Also in this case, the electron domain geometry will always equal the molecular geometry. If my electron domain geometry is linear, my molecular geometry also has to be linear if I have 2 electron domains. There is no discrepancy here. All right, we're moving one down the table now. Now I've got boron trifluoride and I've got nitrite, the anion. So the first step to figure out the electron domain geometry and the molecular geometry for both of these. All right, boron, as we already said, has 3 valence electrons. I have 3 fluorines with 7 electrons each, so that's 21 electrons, 24 electrons to assign. Nitrogen has 5 valence electrons. Oxygen has 6 valence electrons, so 2 oxygens at 6 each, that's 12 valence electrons. And then the -1 charge means I have 1 extra electron. So that would be 18 electrons I'd have to assign for the nitrite. So the boron trifluoride, boron in the center, I just assigned 6 electrons, right, when I made those covalent bonds to fluorine. So there's 6 electrons assigned. Now I need to assign 18 more. Fill the octet for fluorine. So there's 6, there's 12, and here's 18 valence electrons. For the nitrite, I'm going to put nitrogen in the center, and I'm going to put oxygen and oxygen. Okay, so now I've assigned 4 electrons. I have 18 more electrons to go. Well, I'm going to make a extra double bond to one of those oxygens. Now I've assigned 6 electrons. I've got 12 more to go. Now I want to start filling the octet for some of those oxygens. So I need to assign 12 more electrons. Here's 1, 2, 3, 4, 5, 6. This oxygen has a full octet, 2 bonding, and then 6 lone pair electrons. The other oxygen already has 4 electrons assigned to it, 5, 6, 7, 8. So now I've filled the octet, and now I've assigned 16 electrons of the 18. I've got 2 more electrons to assign, and if I look, the central nitrogen only had 6 electrons. So I put those last 2 electrons on the central nitrogen. Now nitrogen also fills the octet rule. It has 8 electrons assigned to it. Now to figure out electron domain geometry. Well, for the electron domain geometry, I have for the boron trifluoride 1, 2, 3 domains. For the nitrite anion, I have 1 domain, I have 2 domains, and I have 3 domains. I've got 1 single bond, 1 lone pair, and 1 double bond. So both have the same electron domain geometry, right? They both have 3 electron domains, so both are trigonal planar. For my electron domain. However, for my molecular geometry, they are different. If I go over here, I work my way all the way across. If I have 3 domains and all 3 of those domains are bonding domains, then yes, I am trigonal planar for both my electron domain and my molecular geometry. However, if I have 3 domains and 2 are bonding, that's what we see with nitrite, and 1 is non-bonding lone pair of electrons, then my molecular geometry would be this bent geometry, changing the shape of the molecule, making boron trifluoride a different shape than nitrite. Here's one more example that fits in that group, phosgene. So if I look at phosgene, I have 1, 2, 3 different electron domains. So based on those 3 electron domains, they're all bonding domains. My electron domain geometry and my molecular geometry would be identical. Both would be trigonal planar. So that means this molecule will be a flat molecule where I'd have approximately 120 degree bond angles, right, from chlorine carbon to chlorine or chlorine carbon to oxygen. Because if I have 3 things attached to that central atom, what's the best arrangement in space to get those 3 objects as far apart as possible? 120 degrees. The next group are 4 electron domains. We're going to talk about tetrahedral, trigonal pyramidal, and bent geometries from the 4 electron domain geometries. And we're going to look at 3 different examples. We're going to look at methane, we've already looked at ammonia, and we're going to look at water. So the first step, draw the Lewis structure for each of these. So methane, carbon has 4 valence electrons. I have 4 hydrogens at 1 electron each for a total of 4 electrons. I have 8 total electrons to assign. I'm going to put carbon in the middle. I'm going to assign all of my hydrogens. So 1, 2, 3, 4, 5, 6, 7, 8. I've assigned all of my electrons. If I look and count, I have 1, 2, 3, 4 electron domains. They are all bonding domains. So my molecular and my electron domain geometry, electron and molecular geometry are tetrahedral. All right, my bond angles are going to be approximately 109.5 degrees. I have 4 electron domains. All 4 of those electron domains are bonding domains. My electron domain and molecular geometry would be tetrahedral. We've already worked through ammonia earlier today to see that ammonia is trigonal pyramidal. Nitrogen has 5 electrons, 3 hydrogens with 1 electron each. Gives me a total of 8 electrons I have to assign. So that looked like this. There's 6 electrons right there, 7 and 8. So I've assigned those 8 electrons. I have 3 bonding domains, 1, 2, and 3, and 1 non-bonding domain. So my electron domain geometry would be tetrahedral. And my molecular geometry would be trigonal pyramidal. The last one, I'll let you work through water. So what would the electron domain and the molecular geometry for water be? So oxygen has 6 electrons, and then I have 2 hydrogens with 1 electron each. For 2 electrons, I have 8 total electrons to assign. I'm going to put water in the middle. Hydrogen, I just assigned 4 electrons. I have 4 remaining electrons. 1, 2, 3, 4. So for water, I have 2 bonding and 2 lone pair electrons. So I still have 4 electron domains, right? 1, 2, 3, and 4 electron domains, 2 bonding and non-bonding. So that means my electron domain geometry is still tetrahedral because I still have 4 electron domains. However, my molecular geometry now is bent because only 2 of those domains are bonding domains. So even all 3 of those have the same electron domain geometry. All 3 of those are tetrahedral with respect to the electron domain geometry. They do have different shapes and they do have different bond angles. And the reason for those different bond angles is simply because of the space needed to take up for those lone pair electrons. So methane has 109.5. We see that bond angle get a little bit smaller for ammonia. It goes down to 107, and that's because of the lone pair electrons. The lone pair electrons take up more space than a bonding pair of electrons. And so because of that, because they take up more space, they're going to have a larger effect on the nitrogen-hydrogen bonds, pushing them farther away from the lone pair electrons and closer together. And that's why we see the bond angle go from 109 to 107. And then we see that in water, it goes even further, goes down to 104.5 because now I have 2 lone pairs of electrons that are taking up more space and pushing the oxygen-hydrogen bonds closer together.